Okay folks, so hopefully you took some time to read section 5.4 before watching this video and you learned a little bit about strong induction. And in this first problem here together we're going to work on the theorem 4.3.4, which states that any integer greater than 1 is divisible by a prime number. We saw this theorem earlier in the semester, but we didn't actually prove it. We said that we're going to leave it for another day, and today is that day. So I'm going to walk you through the theorem, or the proof rather, using strong induction. So again, because I'm doing a proof by strong induction, I'm going to start by saying that at the very top, and that's what I'm going to be looking for on a test also. If you are doing a strong induction proof, I want to see those words. And in this particular problem, the n that we're working with is any integer greater than 1, and so I'm starting with let n be an integer that is greater than or equal to 1, or sorry, greater than 1. And so the base case when n is 2, we can see that 2 itself is prime, and by the way, 2 divides 2, so the theorem is actually true because we're claiming that any number greater than 1 is divisible by a prime number. So 2 is prime, it divides itself, so the theorem works. So nothing to do there. We're moving on to inductive hypothesis. So what are we doing with the inductive hypothesis? In the inductive hypothesis, we're saying, suppose that every integer greater than 1, but less than or equal to some number k, for some k that is an integer, is divisible by a prime number. So basically we're assuming that the theorem works for every integer between 1 and k, sort of. Okay, so that's the main difference between strong induction and weak induction. With weak induction, we just assume that k itself can be divisible, whereas with strong induction, we can make the assumption that every number from 1 to k can be divided by a prime number. So that's what I'm pretty much saying with the blue remark over here. Suppose that every number that is between 1 and k can be divided by some prime. Now I can't tell you which prime it is, but there's some prime out there that divides the m number. So what I would like to know or to show is whether the k plus 1 itself can be divided by a prime number. And this is pretty straightforward. There are two things that could happen to an integer. Either the integer is prime already or it's not. And if the integers are prime already, then you're finished basically. So k plus 1, if it's prime, you're done because it divides itself, kind of like the 2 case. 2 is prime, 2 divides itself, so we were done. So the end of the proof for case 1. The interesting case is case 2, where the k plus 1 is not prime. So what do you do if the k plus 1 is not prime? Well, if you're not prime, then you're automatically going to be called a composite number. And composite just means that you can be written as a product of two integers, where the integers are somewhere between 1 and k plus 1. Okay, so that's what it means to be composite. That means you could be written as a product of two numbers. But let's focus on one of those numbers. Let's say I1, okay, the first integer. Let's focus on I1 and look at what's going on with I1. Well, I1 is automatically between 1 and k plus 1, which means that I1 is greater than 1, but at the same time less than or equal to k. But if I look back at my inductive hypothesis, I assume that every integer greater than 1, but less than or equal to k, is divisible by some prime number. That was the main part of the inductive hypothesis. That is important because that tells me that I1 is now going to be divisible by some prime number. Which prime number? Again, I don't know, but there's a prime number that divides it. And if there's a prime number that divides I1, and I1 in turn divides the original value k plus 1, then because of the transitivity of divisibility, I can say that p divides the k plus 1 term, or the k plus 1 integer. And so we are pretty much finished because we have now shown that k plus 1 can be divided by a prime number. And the problem ends, the proof ends. So QD. Alright, see you in the next video.